Assalamualaikum warahmatullahi wabarakatuh. So, we're from the sixth group, and today we would like to explain about satellite attitude determination, and control systems. But before we start this presentation, let us introduce ourselves. My name is Azai Tawaralai Praputra. My absence number is number 8.
And my name is Naila Reningrum and my absent number is 24.
My name is Sajo Adirio. My absent number is 53.
My name is Yolanda. My number absent 35. So, introduction to satellite attitude, determination, and control system. The attitude determination and control system is a critical subsystem in satellite responsible for determining and controlling and satellite orientation in space. Insecures that the satellite maintains correct position to perform its intended function, such as communication and observation and or scientific measurement. Thanks.
Okay, so next is who designed and built ADCS. ADCS is designed by aerospace engineer and satellite manufacturer, organization like NASA, ESA, and private company. For example, SpaceX and Lockheed Martin. Development customized ADCS for each mission depending on the satellite goals.
Next is the importance of attitude control in satellite missions. This attitude control is vital for satellite operation. Earth communication satellite. It requires the accurate pointing of theirs toward ground station to maintain signal integrity. Earth observation satellites is need stable orientation to capture high resolution image of specific Earth region. The scientific mission it depends on precise alignment to observe celestial bodies or phenomena.
So this is the core components of ADCS. But first, we're gonna talk about the first one, which is the attitude determination sensors. So these sensors help the satellite know its orientation. Here there are a few examples of it. So the first one is sun sensors, which is detecting the direction of the sun. Next one is star trackers, which take pictures of stars to find the exact orientation. And then there's Earth horizon sensors. So this sends Earth's edge to know its position. And then there is magnetometers. So this measure Earth's magnetic field. So it works similarly like a compass. And the last one is gyroscopes or IMUs, which detect turning or spinning motion. And then there's attitude control actuators. So these devices adjust the satellite's position. There are four examples of it. So the first one is reaction wheels. It spin to make smooth and also precise changes. And then there's CMGs. It's like powerful wheels for fast and large moves. And then there's also magnetorques. Yeah, it uses magnetic force to rotate the satellite in LEO. And the last one is the thrusters, which is the small rockets for quick or strong adjustments. So this is the optimal use case for attitude sensors and actuators. So the first component is sun sensors. Sun sensors is effective when in daylight portions of orbit for course orientation. And then there's star trackers. This is effective when in deep space or night side of orbit for high precision. And then there's magnetometers. It's effective when in LEO to sense Earth's magnetic field. And next, there are gyroscopes or IMU, which is effective when always but prone to drift over time. And then there's the reaction wheels. It's effective for smooth and also precise control with low disturbance. And then there's magnetorques, which is effective when in LEO as a low power method using Earth's magnetic field. And the last one is the thrusters, which is effective for rapid maneuvers or momentum dumping in larger satellites.
So the next one is the application of ADCS in different satellite mission. The first one is Earth observation satellite, for example, mapping and surveillance. Second is astronomy mission, for example, Hubble Space Telescope. Third is communication satellite in GEO to maintain antenna alignment. Fourth is interplanetary spacecraft for navigation and communication. And the last is CubeSats with advanced payloads.
The next is how ADCS operates. Step 1 is sensing. Satellite use sensors like sun sensors, star trackers, gyroscopes, and magnetometers. This device collects data about the satellite's current orientation in space. Step 2, processing. Onboard computer or flight software process the sensor data. It compares current orientation with the desired altitude or mission requirements. Step 3, decision making. Control algorithms calculate how much and in which direction the satellite must rotate, determines which actuators to activate and by how much. Step 4, actuation. Actuators such as reaction wheels, magnetor wheels, or boosters are activate. This device generates the cue to adjust the satellite's orientation. Step 5, finally, feedback loop. System continuously monitors and readjusts to maintain correct orientation, ensures real-time correction for stability and accuracy. Next.
So this is the conclusion and future perspective. So ADCS is indispensable for the successful operation of satellites, ensuring they maintain the correct orientation to fulfill their missions. Advancements in sensor technology, control algorithms, and miniaturization continue to enhance ADCS capabilities, enabling more complex and precise satellite operations in the future. So I guess that's enough from us. Thank you for listening to our presentation. I hope you can get a thing or two from our presentation, and I'm sorry if we've made some mistakes during presentation. Wassalamualaikum warahmatullahi wabarakatuh.
Warahmatullahi wabarakatuh.